Today we're going to talk about kinetic energy. The variable for kinetic energy can be written as Ke, or you might see just a K. Either one is acceptable. The equation for kinetic energy is 1/2. The M stands for mass, and the V will be velocity squared. It's only the velocity that gets squared. And the units for kinetic energy will be joules, just like any type of energy or work. They all have the same units. Now I have a question for you about kinetic energy ever being negative. Remember when we talked about gravitational potential energy, that depending on the reference point, potential energy could be positive or negative, but let's look at kinetic and see if the same thing applies. Now kinetic energy is moving energy, so we're going to look at the equation. Can mass ever be negative? The answer is no. Can velocity be negative? Yes, it can, because velocity is a vector quantity. However, look right here. See how it's squared? What happens when you square a negative number? Good, it becomes positive. So no matter what, even if we do have a negative velocity, because it gets squared in the formula, kinetic energy will still turn out to be positive. So our answer right here, no, kinetic energy cannot be negative. So we have a couple of practice problems. First, we've got a 5 kilogram ball. Hopefully you recognize by now that kilograms indicate mass. It is traveling at 6 meters per second. And notice there's no plus or minus sign mentioned. A lot of times, even though technically it's velocity squared, we will see the speed or the scalar version of that as well. So it's okay that we only have a magnitude given. So we're going to go ahead and write that number in. And you are asked to find the kinetic energy. Well, we're just going to take that formula, either K or Ke, and that's equal to 1/2 mv squared, and we're going to plug our numbers straight in. So the mass is 5 kilograms, and then our speed is 6 meters per second, and then we're going to square it. When you type into your calculator, make sure that you only square the velocity. You should get an answer of about 90, and remember that the units will be joules. Now for the second problem, it's asking you if the velocity doubles, what's going to happen to the kinetic energy? Well, you could plug in the same mass that we had before and then double the velocity and plug those numbers in and see what happens, or we can just look at the formula. So the mass isn't changing. We're not going to look at that at all. But if we looked at how the kinetic energy changes only based on the velocity, remember back in chapter 1 we had the is proportional to symbol right here. If I were to look at only the velocity changing and I were to double that, notice that it is squared in the formula. So I would square that coefficient, and this gives me a factor of 4. You should see that the kinetic energy increases 4 times of the value that we had in the above problem. So let's just plug in the numbers and double check and see if that's correct. So if you were to plug that in, you would see that we get a new kinetic energy value of 360 joules. And look, that number is 4 times as big as what we got in number 1. So this type of question, you can work either with the proportionality, or you can actually double that number and plug in a value and see how it changes in that way. It's really up to you. Our next example problem is still going to be the same formula. However, we are asked to solve for the velocity instead of the kinetic energy. So we're just going to plug our numbers into a different spot. You could rearrange the formula for velocity first, or you can plug your numbers in and then rearrange. It's up to you. So I'm going to put my 3 joules in for the kinetic energy. The 2 kilograms we know is going to be a mass, and then we're looking for the velocity squared. Now in this case, the 3 joules are going to stay the same, and you should see that the 1/2 and the 2 are going to cancel. So that's going to leave me with a kilogram and then velocity squared. So if I divide both sides That's going to leave me with 3 over 1, which is just 3, and that's equal to velocity squared. Now, if I were to look at the units and plug in everything for a joule and reduce that down into terms of kilograms, meters, and seconds with our fundamental units, I would have had meters squared over seconds squared, which is good because I want to take the square root of the v squared and also of this other side. And in this case, we don't know if it's positive or negative, so it's fine to use the speed or the magnitude only of that velocity and just say 1.7 meters per second. Now for this section, it does say demonstrations to be done in class, so we are going to go through some of these together. And I just wanted you to think back, however, to when we had that big giant pendulum hanging in the room and we pulled it back and then let it go. Remember, a lot of you guys held that up to your face to see if it would swing back higher or lower to the original position that we started in. So we are going to do these together in class, so I'm going to go ahead and skip ahead to letter F on the work energy theorem. The actual theorem is stated for you. The net work, remember net means total, done on an object equals the change in kinetic energy or in the change in potential energy for that object. So let's write that as a formula. So we would say W for work, and that's going to equal the change in kinetic energy or a change in potential energy. So we set all three of those things equal to each other. So let's apply this in some example problems. We're going to start out with a 110-gram hockey puck. Notice that we need to change grams to kilograms for our mass. You should know by now that that means we're going to divide by 1,000. A player exerts a constant force of 4.5 newtons, and that will be over a distance of 0.150 meters. Now we are asked to find how much work is done. In this case, we don't have any energies yet, so we can't find a change in energy, but we can use our work formula to find how much work the player does on the puck. We're simply going to multiply the F and the D together. So pause the video and try this out and come back and see if you get the same answer I did. Okay, you should have gotten about 0.675, and I hope you remembered to put the units in, which will be joules. Now for part B, what is the change in the puck's energy? So was the puck still or was it moving? Well, we see in the problem that it was sliding, so our change in energy is going to be a change in kinetic energy, and from the work energy theorem, we know that the work is equal to the change in kinetic energy. So our final answer is just going to be what we got in part A. That seems easy enough. Now let's do part C. The puck did start at 0, so we know that the initial kinetic energy would be 0 as well. If there's no velocity, there's no kinetic energy. But at the end of that force being applied, it does have a final velocity and a final kinetic energy, and that's what we're going to be looking for. So I did indicate that my change in kinetic energy is final minus initial. The initial is going to be 0, and I used subscripts for my final kinetic energy and my final velocity to see what the velocity of that puck is after it's been hit. So we plug our numbers in, pause, and come back and see how you did. You should get an answer of about 3.5 meters per second. I did go back and write in some steps for you, but if you're having any difficulties, make sure you come in and ask for help. We can go over this together. We've got one more example problem, so I will get you started, and then I'd like for you to try it on your own and check your answer. You should have identified all of your variables like I did. Now we're going to look at the force that the hammer exerts on the nail. We need to use the work energy theorem because we've got a force and a distance right here. So we need to figure out how much the work is, and we do have enough information to find a kinetic energy, so that can give us the work. And again, we know our initial kinetic energy is going to be 0 because the hammer was moving with a final speed of 3.2 meters per second. So that tells us that our work is going to be equal to the final kinetic energy, and you can plug your numbers in and get a value for that. Now that we know a value for work, we can use our work formula to figure out how much force was applied. I hope you remembered to change millimeters to meters, and that should give us a force of about 717 newtons. Just as a side note, I'm going to show you another way you could have worked this problem. If you are more comfortable with kinematics and Newton's second law, you could work the question that way as well and come up with the same answer. It's a good way to check your math. So let's say I wanted to find the force a different way. Some of you guys might go straight to Newton's second law and say F equals ma. We're given a mass, but we don't have an acceleration. You could have used kinematics to find out that number. It would be the third kinematic equation, which is Vf squared equals Vi squared plus 2AD. You could have used that, solved for the acceleration, and then plugged it in up here, multiplied by the mass, and come up with your force that way. It's just an option for you. I've got just a few more pieces of information for you, and then our last lesson will be some example problems to tie it all together. So for this section for right now, we're going to look at the formula for conservation of energy. The actual law states that energy can change form, but the total amount of energy is constant. So in our example problems that we're going to do in class, we'll see that energy can change back and forth between potential and kinetic, but if you add those together, the total is going to be the same. And mathematically, we would write that as this formula. The initial potential energy plus the initial kinetic energy would equal the final potential energy plus the final kinetic energy. And I do have a question for you. If you think about riding a roller coaster, which hill in the roller coaster should be the tallest? Hopefully you answered that it would be the first one. And the reason for that is as follows. You're almost at rest at the top of your roller coaster, so let's draw a little picture. The roller coaster is almost at rest up here at the top, so that would give it all gravitational potential energy. As it goes down the hill, it loses some of that potential energy, but do you go faster or slower as you move down? Well, you go faster, so that means it's gaining kinetic energy. The potential and the kinetic are exchanging with each other. If any hill were higher than the first one, that potential energy needed to reach that same height, that top of the hill, would have to be stored in the roller coaster at the very beginning of the ride. Think about the pendulum that you guys did in class when you held it next to your face. It's not going to go any higher than that highest point that you started with. A roller coaster is the same thing. So we have this idea of conservation of energy. We're not actually going to lose any total energy except maybe to friction, but all of that energy that the roller coaster needs for the rest of the ride comes from what it gets at the beginning. That's it for today. The next lesson will cover different types of collisions, so we're going to revisit those a little bit and talk about what type of energy gets conserved for both types of collisions, elastic and inelastic, as well as work due to friction. And then we'll follow up with some example problems. Good luck, and I'll see you next class.